Thank you for the introduction and for the opportunity to present here my work. Obviously, it is not only my work. It was done in close collaboration with Richard Anderson, and also it would not be possible to accomplish the numerical models, because I am going to present mainly numerical models without the consultation with Sverre Arzet and also Pavel Kroupa.
It doesn't work because I need to plug it in.
Sorry.
Probably. Let's see if it's...
Ah. Maybe let's type this one. Oh, I might be doing something wrong, but I'm sorry for that. So at the beginning, what are Cepheids? These are stars which at solar metallicity evolve from stars of this mass at the mass interval at the 0-age main sequence. For simplicity, because we will speak a lot about these stars, we will call them prospective Cepheids, or they will be noted pro-Cephs on the plots. This mass range roughly corresponds to mid-B stars of spectral type mid-B. They also go towards early B stars a bit, but most of them comes from mid-B stars. Of course, this is for solar metallicity, but even in our local group, we have stellar systems with different metallicities, like the Large Magellanic Cloud, for example, or Small Magellanic Cloud, which has metallicity around 1/6 of the solar metallicity. And in these lower metallicity environments, Cepheids come from stars which are a bit less massive than in the galaxy, so they can go lower. And it means, because lower mass stars are more numerous than more massive stars, that in these lower mass environments there is more Cepheids than in the Milky Way per given number of stars. So from this point of view, this lower metallicity, this is another reason why lower metallicity environments can be interesting for this study as well. So this is how these stars evolve on the Hertzsprung-Russell diagram, depending on their initial mass. And we see that after they start helium burning in their cores, they just do loop and go increase their temperatures and cross this area on the Hertzsprung-Russell diagram, which is called instability strip. And of course, the evolution depends not only on the stellar mass and slightly also on the metallicity, but also on the initial rotation of the star. Because generally stars which rotate a lot, and there is evidence, or it is clear that many mid-B stars are fast rotators. They are significantly elongated. They are almost rotating at the critical speed. For example, Achernar is one example of B-type stars. So there is these stars which rotate live for longer than non-rotating stars. They can live by 50% longer. So their evolution is slightly different, and they also have a different trajectory on the instability strip. And when they are located at the instability strip, they pulsate. And the remarkable property of their pulsation is that there is a tight relationship between their pulsation period, which is easily accessible from observations, and their luminosity. And if we know their luminosity, their absolute luminosity, and obviously also the observed luminosity, we can calculate the distance, and they are used for measuring distances to other galaxies, for example, and then for calibrating the cosmological distance ladder. Another interesting property of mid-B star is their multiplicity, or the frequency of their companions. Mid-B stars which evolved towards Cepheids are usually observed that they have at least one companion. Sometimes they have two companions. On this plot, we show the number of companions per primary star as a function of the mass of the primary. So for solar type star, there is around probability of 50 to 60% of having a companion. But when we go to mid-B stars, there is already, or most of them have on average around one companion. Some of them, the early type B stars, have on average maybe 1.6 companions. So the remarkable property, another important property of Cepheids, of stars which evolve to Cepheids, is that they start on their main sequence not only as single stars, but they usually, in most cases, they have a companion. And during the evolution on the after main sequence, the primary mass increases, it's reduced. So therefore, if the companion has orbital period of roughly shorter than 200 days, there is high probability of mass transfer, or they can be merged with the Cepheid, or the star which has the ability to evolve to Cepheid, and this can influence the fate of the star and their ability, whether it can become a Cepheid or not, because it can, for example, it can be stripped by its companion, and because of that it would not become a Cepheid, even though it formed on the 0H main sequence with the correct, within the correct mass interval to become a Cepheid. So it is necessary to take the ability to interact with their companion into account as well. And now maybe to the more interesting and fundamental properties of Cepheids, because so far we spoke about mid-B stars. So there is the Leavitt's law, and this is also cornerstone for the establishment of the or calibration of the cosmological distance ladder for supernovae 1A, for example, to distance to the supernovae 1A, and therefore of determining their absolute magnitude. More importantly, when we want to determine the distance to Cepheids, the best candidates are the Cepheids which are located inside open star clusters, because when we know that the Cepheid is inside the cluster, there are many other stars around. So therefore, when we determine the distance towards the cluster, towards the Cepheid, we can calculate the distance also to the many stars around, and then calculate the mean. So it is the distance can be measured with higher accuracy. So for this reason, the Cepheids located inside open star clusters are of particular interest. Another good property of Cepheids is to try to measure the companion frequency to them, or the number of companions, because main sequence mid-B stars usually rotate fast. And therefore they have wide spectral lines. But as they become Cepheids and they increase their radii, their rotation obviously slows down, and therefore their spectral lines are narrower, and it is more easier for them to detect a companion, particularly the one which is fainter or more distant, that the velocity difference is lower. Yes, but there is the complication that Cepheids are not already on the main sequence. So if we measure the number of companions to Cepheids, it might differ from the companion frequency to 0H mid-B stars, because of stellar evolution and the interaction with their companion, but also because of cluster dynamics. And this is what I would like to mention later. Because most of the stars form in clustered environment. They don't form isolated. In particular, early type stars which evolved to Cepheids, they don't form in isolation. So for example, this is very old observation, but I think it is one of the first observations of embedded star clusters. So here it is in I band, and we don't see many stars, but in K band at 2.2 microns there is a star cluster, and we clearly see that the young star objects are clustered, and they concluded that already in this year that from 60 to 95% of stars form in star clusters. And this picture was corroborated by more recent works as well. For example, this is observation of the star formation in the Orion. Here is the well-known Orion Nebula cluster. But apart from them, which definitely there is the famous trapezium multiple stars, which is obviously gravitationally bound system. But apart from that, it is clear there are many embedded open star clusters. For example, this one, and we see that the star formation is clustered. The stars, young stars, are not uniformly distributed, and this is even more pronounced for early type stars. They usually form with other stars, and as they form in gravitationally bound system, they interact with each other just as almost as point masses. But if they form as binaries, they can exchange the companion with another binary or another single star, or the binary might get disrupted. And this is what happens, and this is what we want to quantify in our study. Sorry. And first, what is observed about Cepheids in clusters? How many of them? So in the Andromeda galaxy, the fraction of Cepheids, all Cepheids located in star clusters, or which have star cluster identified, is around 2.5%, which was found by Richard Anderson and his collaborators, which is significantly lower than in the galaxy or the Magellanic Clouds, where in these three galaxies the fraction of Cepheids which are located inside cluster is higher. It is almost by factor of 4 higher. More recently, the fraction was increased a bit, maybe by 1% in the Milky Way because of the most recent Gaia data, simply because it was possible to find more open star clusters, and therefore some of the Cepheids which were previously identified as in the field, people suddenly realized that they are located in a cluster. So for this reason, it is possible that the fraction of Cepheids in clusters is a bit higher than this value. Why it is important, apart from the fact that we can identify Cepheids in clusters and measure distance to them, it is to the bias, to the Leavitt's law. Because if the Cepheid happens to be located in the cluster, and the cluster cannot be resolved, the distance is of the order of 10 megaparsec or further away, then the telescope detects the light not only from the Cepheid, but also the background light from the cluster. And therefore, the Cepheid looks brighter than it is actually. And because it looks brighter, we think that it is further away. And because we don't know the redshift of the galaxy, we would place it closer towards us, and therefore we would end up with a higher value of the Hubble constant. That we would think that the Cepheid is receding from us too fast, because we would underestimate the distance. So for this, it was suggested that it is important to determine this number, also to know the possible bias to the Leavitt's law. So for this, we performed n-body models. So we did theoretical study. We wanted to set the open star clusters as accurately as possible, and then evolve them in a numerical simulation for 300 million years, which is the time at which the least massive star, which is expected to evolve to Cepheid, which has mass at 3.2 solar mass at the metallicity of the small Magellanic Cloud, that this star becomes a Cepheid. And the stars which are of lower mass cannot become Cepheids. And then in these simulations, we quantified various properties of Cepheids, and one of the most important of them is the fraction of Cepheids located in clusters, because the clusters evolve and they dissolve in the field of the galaxy. So in order to perform the simulations, we used code NBody6, and we generated the clusters from this mass range. And we always increase the mass of the cluster by factor of 2, and we assume that the initial cluster mass function has a slope of -2. So it means that at each mass bin there was equal mass of stars. This mass range of clusters corresponds to the mass of young star clusters forming in the Milky Way galaxy as well as in the Andromeda galaxy. So this should match rather accurately the initial conditions for open star clusters. We assumed with agreement with previous observational works that all mid-B stars form initially in binaries. So we generated a companion for each of them, and we calculated 5 sets of models. So at the solar metallicity, we calculated the clusters at these 3 values of galactocentric radius, and also for the radius of 8 kiloparsec, we used these 3 values of metallicity. Each of these 5 sets consists in total of 10 to 5 solar mass. It has 511 clusters, and they form, depending on metallicity, from 1,700 to roughly 3,000 Cepheids. So we wanted to produce several thousand of Cepheids in order to have good statistics, in particular to their companions. This is of the order of number of Cepheids which is known in the Magellanic Clouds. So the statistics should be of the same order as the statistics, as the observational statistics. So perhaps I should show that the star clusters are a highly dynamic environment. So for illustration, I will show this movie. So the movie is for 3,200 solar mass cluster at the beginning, and the stars, which are prospective Cepheids, are marked red. So they will evolve with time over the tens and hundreds of million years to Cepheids, and this is just their position, and these are the views from the same direction, but the only difference between these 4 panels is the scale on this axis, because we will see that there are stars also which are ejected from the cluster, and we included there something which is called gas expulsion, because we assume that the cluster is embedded during the first 0.6 million years, and then the massive stars drive photoionizing radiation and winds, and they expel the star-forming gas. So there is also gaseous potential at the beginning, which is made more shallower with time. So we will see that many stars escape the cluster just due to the change of the potential of gas. This is this moment. This is the tidal radius of the cluster, so the stars which flow over tidal radius are already subjected to the gravitational field of the galaxy. So here we see that the massive stars were retained in the cluster center. Some of them later become Cepheids, and some of the stars which later become Cepheids were ejected from the cluster or just escape at slower speeds. So so we already see that, maybe I will show it once again. The simulation ran for 300 million years. I am showing only the beginning of that. But we can see that the position of the stars which later become Cepheids evolve a lot, and some of them are ejected and they escape to distance of hundreds of parsec from the cluster. So some of them are still retained, but many of them are already at this young age outside from the cluster. Thank you. For this, the code enables tracks of stellar evolution. So this shows the evolution of 4, 7, and 10 solar mass stars at 3 values of metallicity. And that is the instability strip as calculated by Anderson and co-authors in 2014. So the code automatically detects that as the star evolves from the main sequence, which is 0H main sequence for the 3 metallicities is sketched here, that as it evolves and crosses the instability strip, then it records now the star is Cepheid. Then, when it is here, it is not a Cepheid, but as it crosses the instability strip, we say yes, the star is Cepheid, and we record the properties of the star when it occurs that, so it is done automatically. The code also enables more complicated cases, for example, when there is a merger with the companion or mass transfer. So in this case, as the star increases radius, is merged with its companion, and radius increased. And because its mass increased, and therefore it didn't become a Cepheid, and it was not recorded as a Cepheid because Cepheids need to come to the instability strip from lower temperature than is the red edge from the instability strip. Also, there is another event, but which still enabled the star to become a Cepheid. In this event, there was a merger of star of initial mass below the mass limit for Cepheids. And because of the mass gain, the star increased its mass and became a Cepheid. And the code also handled these cases, and we found that around 15% of stars which become Cepheids evolved from the stars below the lower mass limit for Cepheids. But they increased the mass due to interaction with companion. In some cases, this was they were secondaries and also got masses, but they are not that numerous. But the code detected them as well. So this is the fraction of stars, fraction of Cepheids, which occur inside star clusters as a function of the initial mass of the star cluster. So these are the most massive clusters, and around 60% of Cepheids which form in massive clusters are still located in massive clusters, while for example 100 solar mass clusters, it is only around 25% of Cepheids which were formed there, that they still were located in the cluster. 70% of them were ejected, and they become Cepheids at a distance larger than 10 or 20 parsec from the cluster. And these curves are for different galactocentric radius and for different metallicity. So I think maybe we will integrate these curves to obtain the total number, because we didn't see here that much trends. Obviously, as we expect at shorter galactocentric radius, the fraction of Cepheids in clusters is a bit lower than at larger galactocentric radius, simply because in the inner galaxy, the star clusters are disrupted faster, so therefore more Cepheids is released from star clusters. Also, in the lower metallicity, the Cepheids occur at a later time than at the solar metallicity, on average. So therefore, the clusters are more destroyed by that time, and also the fraction of Cepheids in clusters decreases with increasing metallicity. With decreasing metallicity. But it is possible to see it here, but it is not order of magnitude difference. So this is not likely to explain the difference, for example, between the much lower fraction of Cepheids in clusters in the Andromeda galaxy in comparison to the Milky Way. This is the fraction of Cepheids in clusters, but now on the x-axis is the mass of the Cepheid. So the more massive Cepheids are more likely to occur in clusters than the lower mass Cepheids. And this is because these Cepheids, which have also longer orbital periods, longer pulsation periods, come from massive stars. So therefore, at the younger age, the clusters there is still more star clusters than for the lower mass Cepheids, because this occurs at the age of around 200 million years. This occurs at the age of maybe 40 million years. So more clusters, this reflects the destruction of star clusters. That's nothing related to stellar evolution and lower metallicities, apart from the fact that the stars become later Cepheids. here, and the difference is by factor of maybe 30 to 40%. This is the fraction of Cepheids inside star clusters as a function of the age of the cluster. So for the most massive star clusters, this is for the solar metallicity and this is for subsolar metallicity. But the differences we didn't detect practically any significant differences with metallicity here. So the plots are practically the same. But for the most massive clusters, the fraction of Cepheids in clusters stays almost constant with time. And that's the highest, that's around 0.6, 0.7. And as we decrease the mass of the cluster, which produces the Cepheids, then we see the trend that the fraction of Cepheids decreases with time in these clusters, because these clusters get more destroyed on these time scales, while most of these clusters survive. This is observational of the same plot as we calculated here. So this is the fraction of Cepheids located in clusters as a function of their age for the 4 galaxies in the local group. And here roughly we see the same trend that the fraction of Cepheids in clusters decreases with time, the same which we reproduced in our simulations. And it holds at all these 3 values of metallicity. But what I would like to note is the scale on the y-axis. That's different by factor of 3. So main results from this this work, which details can be read here, is that most of the Cepheids in the field were formed in the lower mass clusters, not in the more massive clusters. And the long period Cepheids are more likely to be located in clusters than the lower mass or short period Cepheids. With decreasing metallicity, the fraction of Cepheids in clusters decreases, and also when we calculate the number of Cepheids which can be seen in the cluster at a given time, then most of the clusters host at most 1 Cepheid at a given time. And this is also what is in agreement with observations, because in the Milky Way there is only 1 star cluster which hosts 3 Cepheids at the same time. And in our models, and this is where the models differ a lot with observations, is that observationally it is 9% of Cepheids which are observed in clusters. But in our models it is 30%. And it is not likely that it is such a large difference is can be solely explained as observational bias, and that's likely that there is additional cluster dissolution mechanism which is not included in these embodied simulations. Even though we tried to include everything which was in the standard setting, we probably didn't include all of these phenomena. So one of the missing phenomenon is probably interaction with giant molecular clouds. And later we worked on that, and we still pursue this possibility. And now is the second part of my talk, and it is the probability of the companions to Cepheids. So this curve roughly is the orbital period distribution of companions to early type stars. So we see that the short orbital period companions are more probable, and as the stars evolve, obviously the shortest companions, the most nearby companions interact with the star which has the ability to evolve to Cepheids, and which are likely to prevent it from evolving to Cepheid. But there is something more in the star cluster. There are also long orbital period binaries which might get disrupted due to interaction with other stars in the cluster. And this is what we cannot easily estimate unless we run n-body simulations. So as an illustration, I would like to show another movie from the cluster model. I didn't see it here, but I saw that there were 4 movies, but
in the photo?
yes, I thought that there were 4 movies. Yes, thank you. So this is sorry, I uploaded wrong movie. I'm sorry. I think I cannot show it, probably. No, this is this movie, so sorry. This is this movie, and this is much lower star cluster. That's only 100 solar mass cluster, and the dynamical evolution is even more rapid because the relaxation time of the cluster is much shorter for the less massive clusters. So these 3 stars can become Cepheids, but they are all binaries. And all of them have a companion. I think one of them has another star which can evolve to Cepheid, and the other 2 have stars of mass below the Cepheid mass range. So let's take a look how they will evolve in the cluster. And we see that the evolution, the dynamics of the cluster changes its structure on the timescale of a fraction of million years. And here we saw something which is called hardening. So these 3 binaries, which actually formed a sextuplet here. So we see that the semi-major axis or this outer semi-major axis of the bodies shrunk dynamically because its potential energy increased, and then it is the excess energy is carried by lower mass stars which got ejected from the system. But this system got more compact, and later there will be interaction here, and we see this star which got ejected from the system. So now here is a quadruple system, 4 stars orbiting each other. That's hierarchical quadruple. So it is, when we take a closer look, it cannot be seen from here, we see only 1 body, but this is actually 4 bodies. And at the beginning we see 3 dots, but they were actually 6 bodies. But now we see only 2 of them, because the upper one is a binary and this is a sextuplet. And this is a hierarchical binary where these 2 stars orbit each other like that. And 2 of them can become Cepheids, and the upper one also can become a Cepheid. And also, if you take a closer look, you can see that during the dynamical encounter, these 4 stars captured another 3 stars, low mass stars from the cluster. So they will be accompanied by 3 stars. So it is actually a septuplet. Even though we started with binary, on the binaries only, on the time scale less than 5 million years, the dynamics changed so much. You can see here the stars which orbited. They just formed dynamically. And stellar evolution will come to play soon, because I think the mass is maybe of the most massive star. The most massive star now starts evolving out of the main sequence, and it will explode as a supernova. I think it is now on this panel, because the mass changes, so the code has difficulty in tracking, etc. So now that's the neutron star which got ejected, and there was a merger and mass transfer and merger also in this quadruple. While this star is receding, so we would see that when this star becomes a Cepheid, it is quite far. It will be quite far away from the cluster. So here we took a look at the evolution of binaries, because we see that the semi-major axis can change significantly during these exchange events. So this is the main question which we posed in this paper. So we assume that all mid-B stars form in open star clusters, and of course there is the external tidal field of the galaxy, and the stars have different masses. At the beginning, this is only just summary of the models. And here is the distribution of the orbital parameters of the binary. So this is the distribution of the mass ratio, which we selected to be uniform. This is the distribution of the blue line is the distribution of the orbital periods, and this is the eccentricity distribution at the beginning. And then we let the stars evolve in the clusters. Also, from observationally, lower mass stars have different orbital period and eccentricity distribution from early type stars, and this is also included, yet it is dynamically not so much important for the purpose of this project. Yes, we use stellar evolutionary tracks and also for binary stars, which are pre-calculated due to Hurley et al. And in comparison, because in these clusters we have binaries which evolve, which can change the orbital parameters due to interactions with each other. So we took a look, or it is interesting to take a look at what would happen if all of these binaries evolved in isolation, that they could not change the orbital semi-major axis and eccentricity for another reason than just stellar evolution. And we call them control models. Sorry. So here we compared the final fate of these binaries when they become Cepheids. And this is for control models, and this is for star clusters. So we see that many of these stars with short orbital periods, this is the original distribution, and the shaded area are the Cepheids, which didn't change significantly the semi-major axis, and which still were binaries. So for the short orbital period ones, most of the objects interacted with their companions, and despite that, the green one still become Cepheids, while the red one didn't become Cepheids. And from them, around 30% of the stars which are prospective Cepheids never become Cepheids, simply because of the interaction with their companion. And here, what is due to the dynamics in the cluster is seen for the long orbit period Cepheids. And it is that many of them are softened or disrupted in the cluster environment, and also some of them harden, and it means that they shorten their orbital period more than factor of 2. We just say that they are either softened or hardened, whether they change the semi-major axis by factor of 2 at least. And around 9% of our Cepheids have another companion than which they formed at the 0H- sequence. So this was possible only due to the cluster environment. So sorry. So this is the fraction of Cepheids with companion as the function of the mass of the cluster. With increasing cluster mass, the probability of a Cepheid to have a companion decreases. And it decreases quite significantly from almost 90% for the least massive clusters to around 40 or 50% for the most massive clusters. And it is because the more massive clusters first live for longer, so they influence the binary for longer, and also they have much higher stellar density. So there is higher probability that the outer companion will get removed from the the binary will get disrupted. The dashed line is for the Cepheids in the field, and also here we only mention the mass of the cluster in which the Cepheid originated. It is obviously cannot be found in the cluster. So this is the histogram of orbital periods of Cepheids in which came from various environments. For all Cepheids, it is the yellow line, But when we take a look at the Cepheids originating from more massive clusters, which is the cyan, they have on average shorter orbital periods. Their orbital periods is median orbital period is significantly shorter than the orbital period of Cepheids, which are located in the lower mass clusters. So the means change by more than a factor of 10 in days. Also, there are Cepheids which have a compact companion, and their orbital, they usually tend not to have distant compact companions. So far we took a look at the orbital periods, but it is also interesting to take a look at the eccentricity. So here we are at the gray points are the orbital period and eccentricity of all binaries which can evolve to Cepheids at the 0-age main sequence. And for clarity, we took a look only at this rectangle. And here we connected the state at the 0-age main sequence with the state of the terminal age sequence. So we just terminated, or we took a look at it shortly before the star evolved towards Cepheids, because then its radius increases significantly, and this would and the evolution, stellar evolution in the binary might play a lot of role. So in order to distinguish what is due to the stellar evolution and due to dynamical evolution of the stars in the cluster, we took at this second state at the terminal age main sequence. And here we connected these two states at the 0-age main sequence and terminal age main sequence. But at the terminal age main sequence, around 90% of the life of the star is already spent. So 90% of the dynamical encounters have been already accomplished. So we think that that's a good representation of dynamical encounters. And this is for the control models, only for isolated binaries. We'll see here what happens in the star cluster. And for this, we see practically no isolation, because for most of the binaries, the Cepheid was the primary. So therefore, the change of the semi-major axis or eccentricity was negligible. But at this time, in the binaries where the Cepheid was a secondary and the primary already lost mass, then this orbital period increased because of the mass loss in the system. So this is trivial. But what happens when we include the rest of the cluster is here. These are the same binaries, and they evolve a lot in eccentricity. So we attribute all the evolution in eccentricity and also usually increase of orbital period. So it means that the binary got softened due to dynamical encounters inside with other binaries or single stars inside the star cluster. So there is migration towards higher eccentricities here. So for example, we found that here, when we calculate the density of states in the period eccentricity plane for standard models, and maybe for simplicity, let's take a look. I have around 5 minutes. So for simplicity, let's take a look only at the upper row only. So we see here that here is the number of states to be found at a given area of the eccentricity orbital period plot at a terminal age main sequence relatively to 0-age main sequence. So value of 1 means that there is as many states at the terminal age main sequence as at the 0-age main sequence. And here that's clearly paucity of at this area and excess of this area, which is due to the rapid increase of eccentricity. There are also objects which got captured, like very distant companions, and maybe also some triples, but only dynamically formed triples. And this is what we excluded. It is because this was influenced due to stellar evolution, or can be influenced if the if the Cepheid is a secondary. But there is the clear trend with increasing eccentricity. So we found that, for example, when we see a Cepheid with companion which has high eccentricity, around 0.8, that in 3 cases out of 4, the companion was formed with much lower eccentricity, and the eccentricity was boosted due to the evolution of the cluster. So we suggest that the eccentricity distribution of the companions to Cepheids does not reflect the burst eccentricity distribution at the 0H main sequence. This was significantly dynamically altered. Yes, I think this is the same plot, and this is for cluster dynamics, and this is the mean eccentricity as a function of orbital period for binaries in clusters. And this is the black one is for isolated binaries, where only stellar evolution plays a role. So we see that this cannot be explained, the mean eccentricity from 0.75 and 0.4 cannot be explained by stellar evolution. That's due to dynamics. And this is the number of stars which already become Cepheids by given age. So for the stars which start their mass within the different colors are for different metallicity. So for example, for solar metallicity, all stars become Cepheids by the age of around 150 million years. And then, in theory, there should be no Cepheids after that. But some Cepheids gain mass from their companions. And some stars with mass below this mass threshold can gain mass from their companions, and they can be seen as Cepheids later. And we estimate that the fraction of Cepheids which underwent the mass gain is around 15 to 20% among all of them. So they would occur later than the age of the cluster. So what are also the properties of the companions to Cepheids? So in our models, from 3 to 5% of all Cepheids have a compact companion, which is in most cases white dwarf, but also it can be neutron star, and we also found some black holes in around 4% of the cases. Also, we formed Cepheid binaries in 1.3% of all cases, which is a bit surprising because it is less in what is observed. In the local group, there are only 2 cases, around roughly 10,000 Cepheids, which are observationally. Around 1% of Cepheids have a giant companion, and a smaller fraction of Cepheids, but still there are some of them, have a giant companion, which seems to be much older than the Cepheid, and which points to the fact that the Cepheid is a former merge, and this occurred in a triple. And these are systems similar to this Cepheid. And I think this is the last information. When we started with the assumption that every mid-B star has a companion, so the companion frequency at the beginning was 1, it results in the companion frequency of Cepheids to 0.64. And some of them are binaries in 42% of them, but some of them are also triples. So when we compare this with observations, then the binary frequency to Cepheids is around 80%, and the companion frequency to triples is at least 35%. So the total companion frequency to Cepheids is probably more than 1.15. So I would like to mention here, maybe you are wondering why we want to compare the companion frequency to Cepheids, but we think that Cepheids are very good stars for stars which evolved from early type stars and which are suitable for finding companions, because there is a significant body of work which aims at searching for companions to Cepheids, simply for the fact that they want to improve the accuracy of the Leavitt's law. So, and Cepheids are also much more suitable stars than mid-B main sequence stars for search for their companion, because of their much lower rotation speed. The other surprising fact from our study is that the binary frequency of our models is by factor of 2 than what is the observed value. So from this we suggest that it is not enough that every B star forms just with one companion. They must form with more companions. So when we assume that the dynamical behavior is linear, which is only a rough assumption, it is definitely not linear in the nature. So it means that from companion frequency 1, we get 0.42 for Cepheids. So when we want to get 0.8, we should start with 2. So we suggest that every mid-B star forms with 2 companions. And this is what we would like to explore further in the future. So this is the summary of the 2 main surprises from the study of Cepheids. And first is that, let me to just repeat it once again before I stop, please. So that in our models, around 30% of Cepheids are located in clusters, but observationally it is at most 10%. So it points to a cluster dissolving mechanism in addition to what is already included in M-body models. And the other finding is that our models underproduce the companion frequency to Cepheids in comparison to observations. So, and we suggest that in order to probably to get to agreement, mid-B stars should form in triples or quadruples, and they decay dynamically. Yes, and thank you for your attention, and I am looking forward to your questions.
Thank you for keeping exactly on time. So we have time for questions or comments.
So you mentioned something about the possible bias in the Hubble constant measurement.
Yes.
Did you certainly, what is that?
Because let's consider that the Cepheid has a companion or is located inside a star cluster. And of course, if the Cepheid is located in the Milky Way, we can resolve the star cluster. But if the Cepheid is located in external galaxy far away from the local group, for example at 10 or 20 megaparsec, then we are not able to see, the Hubble Space Telescope can see the Cepheid here, but it cannot see the cluster or its companion, obviously. So we don't know whether such a Cepheid, which was detected by a Hubble Space Telescope, whether there is a cluster around it, small star cluster, basically the remainder of the star cluster, because at the age of the Cepheid, which might be of around 100 million years, most of the cluster can be already disrupted by the external field of the galaxy. So it is not likely to be prominent. So it adds light to the light of the Cepheid. So therefore, the Cepheid looks brighter. And we want to calibrate.
Brighter.
Yes, brighter, because there is additional light from the companion, for example, companion star or the cluster. And if there is additional light, we think, and what is in the Leavitt's law is the difference between the absolute magnitude and the observed magnitude. So the observed magnitude is actually not correct. And we don't see the observed magnitude of the Cepheid, but the combination of the sum of the luminosity of the Cepheid plus the stars around. So we will think that the Cepheid is brighter. And because we know from Leavitt's law its absolute magnitude, we would think that it is closer to us. And but we know the redshift of the Cepheid at the same point. So we will calculate for the calculation of Hubble constant. It is the speed per divided by the distance. And of course we know the speed from the redshift, but the distance is underestimated. And therefore we would overestimate the value of the Hubble constant. And first it was discussed by other authors. They also suggested this project as a motivation, that there is the well-known discrepancy between the value of the Hubble constant, which was obtained observationally, mainly from Cepheids, and which is of the order of 71 or 72 kilometers per second per megaparsec, and the value due from the Planck satellite, which is of the order, which is of 65 and which is lower. So they were first curious whether this can, whether this could potentially solve the discrepancy, but it cannot. The difference is too large.
questions or comments? Frantisek? Well, if anything comes to mind, Frantisek will be around for about 2 years, so we have time to chat with him. So with
Yes,
that, I'll
please.
close the talk and let's thank the speaker again.
Oh, thank you.